A digital device sits at the center of nearly every modern investigation, whether it's a corporate audit or a criminal trial. The entire case often hinges on digital evidence, any electronic information of probative value, meaning it can officially support or refute facts in a legal proceeding. But locating the incriminating data is only half the battle. The facts mean nothing if the underlying bits were mishandled before they reached the courtroom. The instinctive actions of a standard computer user, booting up a machine to look for files or copying a folder to a USB drive, actively overwrite metadata and destroy the legal validity of the evidence. The strength of a digital case relies entirely on the technical methodology used to capture and protect the data from the moment it is found. Every forensic examiner faces a rigorous cross-examination regarding their procedure. Who seized the device? Was it hashed? Was the original protected? If the examiner cannot definitively answer how the data was secured and extracted, the judge will likely throw the evidence out entirely. This legal acceptance is known as admissibility, the threshold of whether a court, disciplinary panel, or audit body officially recognizes the digital evidence as valid. Achieving that admissibility requires investigators to look past administrative rules. They must design their extraction process around the physical realities of how hardware reads and writes data. Before a single byte is collected, an investigator must understand exactly how fragile a digital system actually is. Inside a functioning computer, information is constantly flowing between temporary memory, permanent storage, and network interfaces. This diagram shows 5 distinct characteristics of digital evidence: fragile, volatile, duplicable, hidden, and high volume. Because data is physically fragile, simply turning on a device alters the evidence, permanently overwriting unallocated space and altering file creation times. But the most vulnerable information is volatile data. Volatile data is temporary information that resides exclusively in RAM, or random access memory, the short-term workspace for the operating system. Some of the most valuable forensic artifacts live only here, things like active network sessions, running processes, and unlocked encryption keys. RAM requires constant power to hold its state. If power is cut to the system, this highly valuable volatile data is instantly and permanently destroyed. This is the exact opposite of hidden or deleted data. When a user empties their trash bin, the files persist on the physical platters of a hard drive or the flash chips of an SSD until they are manually overwritten by new files. Investigators are caught in a trap. Pulling the power cord perfectly preserves the deleted files on the hard drive, but it wipes the RAM. Keeping the power on saves the RAM, but allows the operating system to continue overwriting the hard drive. This physical reality forces an investigator to make a critical, irreversible triage decision the moment they secure a device at a scene. When an investigator first approaches a suspect's computer during a raid or an incident response, the environment is often chaotic. But the entire forensic strategy hinges on one immediate observation. Is the device currently powered on, or is it off? This diagram illustrates the decision matrix. If the computer is found powered down, the investigator follows the left path to a dead box acquisition. In this scenario, the device remains off, and the examiner performs a physical, bit-by-bit copy of the entire storage medium. This physical acquisition creates a comprehensive replica. It captures all active data, deleted files, and hidden partitions, completely avoiding any alteration to the original system. If the investigator finds the suspect device powered on and running, they follow the right path: live acquisition. Here, the trade-off is stark. Yanking the power cable preserves the hard drive perfectly, but vaporizes the RAM. Leaving the machine running allows the investigator to capture active network connections and encryption keys, but exposes the system to a remote wipe by an accomplice. Performing a live acquisition means plugging in a drive and running extraction software on the active system. This unavoidably alters the very evidence being collected. Every interaction changes the machine. The investigator must meticulously document their chosen method to justify those unavoidable changes to a judge. Once the device is secured and transported back to a sterile forensic lab, the actual data processing begins. The examiner now faces a strict legal hurdle. How do they prove to a jury that the forensic copy is an exact, unaltered duplicate of the original drive seized at the scene? To guarantee this, labs use a two-part defense. The first is a hardware solution, the write blocker. This diagram shows a write blocker placed physically between the original suspect drive and the forensic analysis computer. It ensures data can only be read, intercepting and rejecting any return traffic to prevent accidental writes or modifications. The second layer of defense is purely mathematical, the cryptographic hash. This animation demonstrates how a hash acts as a digital fingerprint for data. Standard algorithms like MD5 or SHA-256 process a file, or an entire hard drive, and output a unique fixed-length string of characters. The rule of mathematical certainty dictates that if the original drive and the forensic image are identical down to the last bit, their hashes will match exactly. The algorithm is hypersensitive. If even a single piece of hidden metadata is altered during collection, the resulting hash completely changes, instantly exposing the tampering. This math dictates the golden rule of digital forensics: securely store the original device and perform all analysis exclusively on the verified forensic copy. Matching hash values provide the technical verification required to show that the evidence remains unchanged from the moment of collection. But technical verification in the lab is only effective if it translates back to the administrative and legal realities of the case. We can now return to the courtroom checklist the examiner foisted at the beginning of the investigation. This diagram connects our technical solutions directly to those legal questions. The hardware write blockers and the hashing algorithms provide concrete, provable answers. Yet there is a remaining human vulnerability. Even perfect cryptographic math cannot save a case if the court cannot verify who had physical access to the hard drive before it was hashed. This requires a chain of custody. A chain of custody is a continuous, meticulously documented record detailing exactly who collected, transferred, analyzed, and stored the evidence from the moment it was discovered. Technical integrity through hashing and human accountability through the chain of custody must overlap perfectly for digital evidence to survive real-world scrutiny. The best practices are clear. Thoroughly document the physical state of the scene, deliberately choose the right acquisition method, calculate integrity hashes immediately, and restrict all analysis to the verified copies. The core tension of the profession lies in the physical nature of data. Digital evidence holds the power to definitively solve crimes, but it takes only a fraction of a second to destroy it by accident. The investigator's mandate is not simply to find proof of guilt. Their job is to objectively uncover and report all relevant findings, documenting both inculpatory evidence that supports suspicion and exculpatory evidence that points to innocence. The forensic examiner serves as the vital bridge between the chaotic reality of a live incident response and the strict, logical rules of the courtroom. A chat log, a deleted file, or a volatile network trace has no inherent legal weight on its own. Admissibility is manufactured entirely through the rigorous, documented, and scientifically sound process of the investigator who collects it.